Hello again. Sorry for lack of activity on the blog. I've had some work commitments I couldn't get round to doing very much. That said, I've done quite a lot, but just in bits and pieces, so I've got enough to talk about it now. So I thought I'd take you through where I've got to. If you remember the last blog, I said that what I'd do next is take it to a PCB. So I've actually done that. This was the first PCB. As I said in the last blog, what I'd do is I'd just concentrate on the control circuitry or the programmable voltage reference. That's essentially what that circuit, what that PCB covers. You'll see on there already there's some breadboard activity. Pretty much the first thing I found in testing around noise was that I really needed to put a buffer in to drive the analog to digital converter. I was hoping I didn't have to do that, but I did have a feeling I might have to. A little bit about the board layout, pretty simple. You'll see there on the right hand side, you can see a microcontroller. All of the digital lines are isolated via 100 ohm resistors there, just to separate the two. And on the back, you'll see that there's very clearly two ground planes. One is the digital ground plane, and one is the analog ground plane. The idea being it's in a sorry about the camera's not quite focusing that well there. The idea being that in the final build, it'll be built around a star-Earth topology, and the two grounds need to be separately routed. What you'll see on this board is that I've breadboarded on, basically just tacked on top a simple voltage follower buffer. I used a microchip parts and drove the ADC, and that improved things considerably. However, I wanted to do more with it, so I've actually, in the same time, I've also built a second version of this, which actually is a second board revision. You can see I've got quite a lot more on there than I had to start the first time. I've actually moved all the error amps and the comparators for the LED status for constant current, constant voltage are all on here. Move things around, condense things up a bit, basically fit more on. And that's the version 0.02 that I've been doing my testing with. Let me zoom in here just for a second. Okay. As one would expect, there's the second board, the Revision 02 board built and installed, and actually you'll see already that I've been hacking on additional parts and changing things around already. Just to give you a sense of what this board looks like and the layout. Again, same microcontroller. These resistors here, all the digital isolation. So there's a fairly nice clean isolation between the digital circuitry and the analog circuitry. And if you look on the back of the PCB, you'll see again a separate ground plane, two separate ground planes, one for the analog and one for the digital. The way I've brought it out, basically that's all the digital signals here, and that's all the analog signals here. The format I've used is similar to a kind of Arduino layout, just two sets of pins. Again, this is all only prototype, so it's not meant to be the finished article. It's simply something to work with. So all of the control circuitry is here. This is effectively a programmable voltage source, I suppose, a precision programmable voltage source. So that's certainly what I'm aiming it for it to be. You can see it's currently running. The blue LED there is flashing status. There's a constant current and constant voltage LED here, which you'll see work in a minute when I turn it on. One of the things I found pretty much straight away was unlike my previous assumption, the input offset voltage of the error amp is actually quite important, and it's important in the design because the design is based on a programmable voltage reference, and any difference on the input of the error amp will actually cause errors on the output. So I've moved away for the error amp from a LM358 to something a lot better, which is an LT1013 dual op amp as well. I've had to graft it in there because unfortunately the pinouts on that chip are different to the pinouts of or that chip as an SIOC 8 device is actually different to the DIP 8 package. So I couldn't put the surface mount version on. I have to rework the board again. Another thing I changed is I'd originally had a transistor in here to deal with shutting off the output. I've changed that to a FET because I was getting some control issues with it. I've actually still got a variation of that problem, so I'll have to look at that again soon. Or there's two voltage regulators. That's the voltage regulator for the digital circuitry. That's the voltage regulator for the analog circuitry. So it's all pretty self-contained. The board it's sitting on, if I zoom out here just a little bit, is a prototype board which has a revised output stage, and I'll talk through that in a second. Has AC in, and that's AC. That's currently about 14 volts AC. Into a rectifier, normal reservoir cap, regulator for the low voltage, obviously driving the output device, which is a different device now, and there's the current sense resistors there. There's the output, and I've got various bits and pieces hooked up to that. Just going to take you through one of the things I found with the circuitry. The original design. If you just give me a second to zoom out here. So the original design was based on this principle, and very simple, very classic, nothing complicated there. Error amplifier, programmable voltage source, negative feedback. You can set the gain here, and pass device. And the problem with that basic design, which is fairly typical of a single chip regulator kind of design, is that the output voltage here is limited to about a little bit less than the supply voltage or the output swing capability of the error op amp. So where I need 0 to 40 volts output, I need a gain of 10 here. Clearly, I'm not going to try to get an op amp with, well, they are available, but it was not how I wanted to approach it. To get a gain, so I have to add gain. That's the basic problem. And of course, so this was a very very rough conceptual design or block diagram of the gain stage, and all that is an emitter follower. There's nothing complicated about it. The issue with this circuit, if you look, the feedback comes around the whole thing. First of all, there's a very very narrow voltage swing here in order to drive this circuit, and as soon as you start putting different types of load on here, especially as the gain increases, you've got different kinds of loads, whether they be inductive or capacitive or resistive. The capacitive effect specifically can very quickly drive this into an out of phase condition, which will cause it to go unstable. And that can be at low frequencies and high frequencies. Typically you have quite large capacitance on the output here, so it can be low frequency instability. So you have to start compensating, and often there'll be this kind of setup where you compensate for high frequency and so on. And it's at gains of 10, it's quite unstable, and it's actually very very difficult to stabilize that and keep the design simple and account for all the variations of output. Load types. So what I've done actually is I built a variation of this. Actually, I changed a few things. First of all, I changed the output device to a PMP device, and actually it's a Darlington device. It's a TIP 147, which is in the current circuit. Same thing, load. Feedback comes back into the error op amp, but there's a big difference in this circuit. We've still got the gain stage. This time I've used a FET, and for those of you that know the difference between a FET and a transistor, this is a voltage amplifier, or behaves much more like a voltage amplifier. And I've used some of my very rudimentary knowledge around valve amplifier or tube amplifier technologies, and I've put some negative feedback in here. So put a resistor down here to 0 volts and a resistor back from the output. Now what this does is this sets up local negative feedback. So although it's not completely linear, it's effectively gives me a gain. I've currently got a gain set of about ×2 here on what I'll be testing at the moment, what you'll see. And the effect of that is it really stabilised the circuitry. In fact, I haven't yet had it burst into instability despite the loads that I put on it, and I'm putting large loads, small loads, capacitive loads, resistive loads. There is a current issue around I can force it to go unstable by putting a very small capacitive load of a certain type on here when there's no other load. But that's actually that only occurs if I don't have the small electrolytic output cap on the output. So other than that, it's been very, very stable. So that's the design as it currently is. Let's zoom back in here. There's something else I wanted to mention just in the current setup. I mentioned a couple of blog posts ago that one of the issues I had was in relation to offsets, and this is particularly true for the analog to digital converter here, because the whole design is built around a single supply. I don't have any negative supplies on the design. The op amps will not necessarily swing right the way down to 0 volts, so the effect is on the ADC. I can see a very, very low offset or a very, very low value above the 0 volts. So to compensate for that and deal with that, I've actually just right now, you can see I've just hooked this in. It's very temporary. It's running off a battery, so it's obviously not intended to be part of the design. What this is doing, this is a very simple rudimentary regulator that's generating a -200 millivolts signal and a power supply. Sorry, and all I've done is powered the 4053 switch, the VEE pin, and the negative supply rail of the buffer op amp with that -200 millivolts, and that's given me enough of a swing to get back down to 0 volts. So that's kind of what the test setup looks like. I'll look at this next time and how I actually implement this properly. My thinking is probably I've got a spare PWM output on here, so I'll use this to drive a charge pump, simple capacitor diode charge pump, and I'll generate a negative voltage from there, regulate it down. Also, the op amp that I'm using to drive the ADC is a microchip part, MCP622. It's limited to a single supply of 2 to 5.5 volts, so actually it's not very flexible. I'm going to also change that for an LT1013 part, so that'll reduce my bill of materials. There isn't actually that much difference in cost between those two parts. So let me just show you this power supply working. I want to talk about the dummy load setup I've got here, or the load setup I've got here. For those of you who know what these are, this is a 50 watt halogen 12 volt bulb. I've got that just hooked up to a small relay so I can operate it with a foot switch. So I can put the load on or off, and I'm looking at the output of the power supply with the scope, and also with the Agilent meter, calibrated meter. So I just want to give you a sense of the resolution and the control over the output. So now that you just saw that number drop there, and the reason for that is I've just put the load on the output, and the power supply is currently switched off. What I haven't got in the design at this point in time is a minimum load on the regulator circuit, which I'll definitely have to put on. But right now I'm using that there. Okay, so what I'm going to do, I'm going to set the output to 2 volts dead, according to my control panel, and then I'm going to turn the output on. And you can see the Agilent is reading really nicely 2.000.54 volts. I'll set it to 4 volts. You can see also the lamp. You should see the lamp is starting to light. Sorry, set that to 3 volts. I'll set it to 4 volts. 6 volts, 8 volts. Okay. Now, if I pick a voltage, and you can see actually there, I'm about a millivolt out at the upper end. I think that's to do with the DAC, and I haven't quite looked into that yet, but I think that's what that's to do with. If I pick any other voltage, I don't know, something like 3.567, just by way of an example, you can see the accuracy and the resolution I'm achieving. One of the other things I had to do on the microcontroller, I was using the microchip MC8 compiler, the microchip compiler, and for those of you that know microchip, they've recently, or not so recently now, acquired High-Tech, and they're moving all their compilers to a unified set of compilers called the XC series. And what was happening with the MC compiler, I'm doing floating point calculations inside the microcontroller when I'm setting voltage, setting current, and actually I was getting floating point errors on the microcontroller, and that was down to the runtime. I recently was at Electronica 2012 in Germany. I spoke to one of the microchip guys there, and he said that he recommended just switch over to the XE series compiler, which I did, and that actually solved that problem. So that's definitely worth noting. The changeover wasn't too bad; it was fairly straightforward, and now at least I can depend largely on the floating point maths. Okay, so in terms of resolution and accuracy, you know, I'm pretty pleased with results. I'm pretty much there as far as the controller. The accuracy I'm able to set, I'm meeting all the objectives I had. Actually, I can get more resolution out of it if I want to, but I really don't need it. That's certainly good enough. I'll show you very briefly what the load regulation looks like, and particularly the very simple example of using looking at what happens to the output when it's turned on into a load. I'm just going to use the scope here in single shot mode. Hopefully we're set up at the right time. So as I turn the output on, so that's effectively me switching it on from 0 volts up to 3.5 volts into a load that's drawing 1.5 amps, and that's what the profile looks like. So it works really nicely. It doesn't overshoot the set voltage. Now if I set the current limit, let me work this back to 1.6 amps. 1.45 amps, sorry. And turn the output off. There you go. So that's the current limiter kicking in, and that's the filament warming up. And I've got the current set right on the borderline of the current required to run the lamp. If I do the same thing again but take the current limit off, so I'll set that to 2 amps. Turn that off, turn it back on, hopefully, if I can get it to trigger. Okay, you can see it much faster. And if I set that up to something like 5 amps, do the same again, you'll see it almost instant. What I'm going to do now, I've shown you enough there. Obviously, the next time I'll cover this circuitry, this generating the negative voltage, and I think I've done enough testing now to be pretty confident that the next thing I can do is actually build the final PCB. Talk a little bit just about the current construction as it. Just turn that off for a second. I'm just touching that heatsink. It's quite warm now because I haven't particularly got a large heatsink on here. Okay, this is the size I'm expecting the module to be. Probably smaller than this actually, but the idea here is you'll be able to mount this on a zoom out just a little bit. In construction, you can mount it like that. I'm going to aim to get the module as small as possible, but obviously without cutting corners mechanically. The mechanical construction needs to be fairly solid, and I'm aiming for this to be completely self-contained. So just as I have it now, AC in, voltage out, remote sense out, and we'll talk about that next time because there's some changes to the circuitry I need to make to support that properly. And yeah, so that's ultimately what the module is going to be like. The current output design as it stands at the moment, I have tested it at the various ranges that I wrote about in the last blog. That was the 0 to 8 volt range you've seen. I've also tested 0 to 40 volt range with times 10 gain, and that also works well. I'm aiming to do that with only having to change a couple of resistors in construction, so you can effectively program the board to the range that suits you and be able to use it. Just a quick demonstration on the load regulation of the power supply as it's implemented now. Right now you're looking at the Agilent meter and the scope. They're both looking at the output of the power supply. It's currently on. It's set to 4 volts exactly. This is set to a volt per division, so you can see the 4 volts here. There's no current, no load on the output. What I'm going to do is I'm going to turn on the load, which is this 50 watt bulb here for the purpose of this test, and you can observe both the voltage output here and the scope to see the effect of placing a load, a cold load, a very low resistive load on the output of the power supply. You saw some activity and immediately there you go. So it's delivering pretty much spot on exactly 4 volts again into that load. And if I remove the load, you can see that the regulation remains there. Now there is an interesting thing. The voltage control is very high speed at the moment, and you can actually see on the scope, if you catch it really carefully, when I remove the load, you can actually see the bounce of the relay contacts, which is turning the load on or off. It's very difficult to catch, but you can definitely see it. So anyway, so that's setting the output with a load on. I'll use this single. What I'm going to do is just turn off the put the load on, turn off the power supply from the software control. So we're now at 0 volts. I'm going to put it into single step mode. Or single shot mode, and you can have a look and see what the power supply, how it behaves when it's switched on and driving into a load. Now there's a couple of interesting things to note about this. First of all, if you look, I'm triggering above this point, so I'm focused here on this center part here. But if you zoom in on that, you can see it's a really nice, works its way up to the desired voltage. It does that in about 20 microseconds there or thereabouts. It's 8 microseconds a division, so it's very fast. I showed you earlier that I used a transistor to effectively clamp the output of the error amp, and what's happening here is when the software turns the power supply back on, is it lifts that clamp, and then the error amp has to kick in and regain control of the voltage before we actually turn on the output. I can't fix that in software. I'll have to change the hardware. In fact, what I need to do is I also need to clamp the input of the error amp to get the error amp in the right condition. I don't particularly want to slow this down in hardware, this rise rate, so I'm actually going to implement some software to ramp this up to get a better control or smoother control on the output. But it's pretty good. As you can see, the load regulation is really spot on. It works really well. It's very fast, and there's no instability in terms of noise. It's nice and clean and does the job. All right, thanks very much.